You guys all, you are already added to this session. So use your right account to access this. Don't try to access from a different account and you need permission,
Yes, sir. So,
interrupting the class.
sir, in the previous class, I didn't need that permission with the same account, with my G Suite account, but in this class, I needed the permission.
Really?
Yes, sir.
There's some problem.
Sir, maybe my G Suite ID also has not been added because when I tried to join, it was asking for the permission.
I think I
Sir,
used
I guess
only, I think I used only the G Suite IDs. I didn't use any other IDs. Yes?
Yes, sir.
স্যার আমাদের যে ক্যালেন্ডারের ইনভিটেশন থাকে ওখানে যদি আমরা ইয়েস গোয়িং এ ক্লিক করি তাহলে আই গেস স্যার পারমিশন লাগে না স্যার জিসুট থেকে।
কি বললে আবার বলো আসতে পারি।
স্যার আমাদের যে ইনভিটেশন থাকে ক্যালেন্ডারে সেখানে যদি আমরা ইয়েস মানে ক্লাসে ইয়েস গোয়িং দিই তাহলে স্যার তারপর যদি আমরা জয়েন করি তখন মেবি আর পারমিশন লাগে না।
Maybe you can try that. So you open your account, open the calendar, and try to access this session from there. Let's send. Okay, I will try to. I will check, and if there are IDs other than G Suite IDs, I will change, replace them with G Suite IDs, and send you the invitation, fresh invitation. Okay, so we'll start our regular lecture now, and first I will share the screen with you. So what is this amplifier configuration? Hello.
So common emitter configuration.
Right, this is common emitter amplifier. And we'd like to determine the following parameters: the voltage gain, which is V naught by Vi, the current gain, which is I naught by Ii, and the input and the output resistances. So what's the first step we need to do here? The first step to analyze the circuit.
So disconnect all the DC sources and short the capacitor.
There are no DC sources here.
Oh, sorry.
We have already done that in the last class.
Then just replace it with the given model.
So replace the transistor with its the what we call the small signal models, hybrid pi or T models. So that is the pi model for the transistor, and then we need to connect the rest of the circuit with this model. We at the input side we have Vs and Rs that is connected to the base terminal. So that is our Vs and Rs. The emitter is grounded, so just ground the emitter. At the output side, we have the load resistance connected. So we connect that one, called the RL. Now, the output current is flowing through the RL, that is called the I, denoted by I naught. At the input side, we have the input current II going into the base. The resistance looking into the base is our input resistance Ri. resistance looking from the output side is our output resistance or not. Somebody is waiting there, I guess. So, question of which. Okay, now the most straightforward here is the input and the output resistance. What is the input resistance in this case? What is the input resistance? Can anyone tell me? RI. It's pretty straightforward, no?
Sir, RS and RPI in series.
What?
Sir, RS plus RPI.
Why RS?
So shouldn't we consider RS?
Why we should consider RS?
Oh, or maybe it is the resistance of the voltage source.
What?
Sir, I'm confused. Should we consider RS or not?
What is RI?
Sir, the input resistance.
Input resistance of what?
Input resistance of the transistor.
Input resistance of the transistor?
Oh, sorry, sir. Input resistance from the base emitter side, we can see.
The parameters that we are trying to determine, these are the parameters for the amplifier, right?
Yes.
We don't say transistor or base emitter, we say the parameters for the amplifier.
Oh, yes.
What is the input resistance for this amplifier, common emitter amplifier? Amplifier that includes not just the transistor, that has those resistors, capacitors, right? That everything together that make the amplifier. It's not just the transistor. The amplifier is represented by this triangle, right? Something like a triangle. This represents an amplifier. It has an input terminal and an output terminal, right?
Yes, sir.
And then you, at the input, you connect the source, right? At the output, you connect the load. The current that flows in the load we denote as I naught, the output current voltage is V naught. The gain of the amplifier we denote by A, or more specifically for voltage gain AV. The current that flows here we denote by I input current, that input resistance. So amplifier can have different configurations, right? Different design. But in general, this is represented by this, and these are the parameters for the amplifiers. So the question is, what is the input resistance? It's the input resistance for the amplifier. And RS, RL, they are not the part of the amplifier, they are external to the amplifier. RS is the source resistance that is associated with the source. RL is the load resistance, though these are not the part of the amplifier. Did you get my answer?
Yes, sir.
Yeah. These are not the part of the amplifier, RS and RL. They are external, right? The input resistance is looking into the amplifier, looking from this point. The RS is, before that. It's not part of the amplifier. So then what will be the input resistance? Yes. Is it very difficult? Very simple circuit, no? You can't have simpler circuit than this. Okay. See, all these are going to ground. So I can also, it doesn't work. Something's wrong there. So all these terminals, they are going to ground, right? So Ri is the resistance between base and ground. So what will be the Ri?
R pi, sir.
It's just R pi, right? Oh, it's not working. I don't know. Oh, this is gone. Ink is there. I don't know. Okay, there's a problem here. It doesn't work. So let's get back. So between this base and ground, right? You're looking into the emitter. Sorry, the base, and the input resistance here is between this point and the ground, right? This point and ground, and this point and ground you have just R pi. You just write that Ri is R pi. Finished, right? And what is the output resistance?
R naught.
Right, output resistance is just R naught, very straightforward. So these are pretty straightforward for common emitter. Input and the output resistance, input resistance R pi, output resistance R naught. These are same as the transistor because emitter is grounded, right? Emitter is grounded, so between this point and ground we just have R pi, and this point and ground we have just small R naught. So because of that we get the same values. Now we'll try to determine the voltage gain V naught. Sorry, AV, V naught by VI. So in order to determine the voltage gain, we start with the output voltage V naught. What we can write for V naught? What will be our gain? Sorry, the output voltage.
Sir, I naught RL.
That is right, I naught RRL. That is the most obvious answer. But if you look more closely, we can have a better expression that will be easy to determine the voltage, more straightforward. What is the other expression we can write for V naught?
GMVBE times R naught.
That's only R naught?
GMVBE
Yeah,
times R naught.
only R naught?
Sir, R naught parallel
Multiplied
RL.
by GMVBRE.
Right. You see, the R naught is, this is in parallel with RA, right? These two are in parallel. And GMVB is the current, right, that is feeding this parallel combination. And I naught is the part of this GMVB. that we also can determine by applying voltage division. We can also write I naught RL, that is also correct. But in that case, then we will have to again replace I naught by GMVBE. I mean, applying the current division rule. Part of this GMV will go into I naught. We need to determine that and replace. So we will have to do a little bit more calculation, right? More steps will be there. But we can straight away write that this is the total current GMVBE, and that is supplying this parallel combination R naught RL. But this will have a minus sign because the current through the resistances will flow upward, right? It is flowing in this direction. So we'll have minus GMVBE, and that times R naught, that is in parallel with RL. So that is our expression for the output voltage V naught. And from this expression, we can write one expression for the voltage gain, that is V naught by VBE, and that is equal to minus GM, and that is R naught in parallel with RL. Is that clear? Now, our actual voltage gain expression, sorry, I wrote the VI, it should be VS. Our input voltage is VS. So our actual gain expression is V naught by Vs. We have, and that is the gain from this point, the input point is here, and to the output point at the collector, right? So if you look at the transistor here, input and the voltage at this point to output voltage V naught, and what we have determined the voltage gain from the base point. VB is the voltage that we have across the base emitter junction. We can have this. It's not working. Okay. Okay, so our voltage VBE is the voltage across this R pi resistance. So that is our base and this is our emitter. So this is our voltage VBE. And we have determined this gain expression, V naught by VB. V naught is the output voltage, and this is the VB is the voltage actually at the base point. So because the emitter is grounded, so it's the same as the voltage at the base. Usually voltage at the base we denote by VB, right? And in this case, VB is same as VBE, right? So VB is same as VB because the emitter is grounded. So here we can write the gain expression. The overall gain is V naught by Vs, and that is equal to V naught by VB and VB by Vs. So we can express this as a product of two gains. One is the gain from this point to base, this VB by Vs. The other is the VB, the V naught by VB. So that's the gain from base to collector, right? So we express this as the product of these two gains. So we have already determined this part, right? So that is this. This is VB is VB. So that is this gain expression. So here we need to determine the third one, the second expression, VB by VS. So what will be VB by VS? Hello guys. What will be VB by VS?
So RS plus R by
RS plus R pi.
into I1 II.
VB by VS. Hmm.
So voltage division rule on VB.
And what you will get?
R pi by R pi plus RS into VS.
Okay, so you apply voltage division rule to determine VB by VS. That is the obvious choice, and you get the straightforward answer. VB by VS is the ratio of this, the resistances R pi divided by R pi plus RS. What did it change? Okay, guys. So now we have determined both the parameters. One is V naught by VB, that is minus GM R naught RL, and that times we have R pi plus RS. Is that clear, guys?
Yes, sir.
Okay. Now, a couple of things note here to note that here the voltage gain for the common emitter is negative, right? The gain is negative. The other is that the first part here, GM R naught R, this is the actually gain, right? Which actually amplifies. The second part here, actually, it is attenuation, right? So this part is less than 1, right? This part is less than 1. So basically, this is not a gain, but attenuation. The signal is decreasing. You lose some signal strength because of the source resistance R pi. So there will be some voltage drop in RS, right? So part of the VS will drop across RL, and then part will appear across R pi. So we lose some signal at the input side. And so the second part is actually is an attenuation. Is that clear, guys?
Yes, sir.
Okay, so then we have determined the voltage gain and now the current gain, right? We determine the current gain. So what is the current gain? So of course, as I said that I naught is a part of this GMVB. To be more accurate, if you apply the current division, then we have minus GMVB, that is the total current, because I naught and GM, this two are in opposite directions, so we put the minus sign, and then R naught divided by R naught plus R. So that will be your the current I naught. Right? Usually the output resistance this of the transistor R naught is much larger than RL, while R naught is in the range of 50 to 100 kilo ohms, and RL usually few kilo ohms. So in most cases, RL is much greater than RL. So if you apply this simplification, R naught much larger than RL, this is almost equal to 1, and this can be approximated to minus GM dB, right? So that will be our I naught minus GM dB. Is that clear, guys? So actually we are ignoring the current that is flowing into R naught because of the high value of R naught. Very small current will flow into R naught, and most of the current will flow into the output rate, the load resistance RL. So I naught will be almost equal to minus GMVD. Now current gain is what we have written here. The current gain is I naught by II, and I naught we have it minus GM so we write minus GM divided by II. And II is the input current that is flowing into the base, right? And that is also the same we can say as the IB. II is the IB, so the resistance that is flowing into the base. So this we can also write as minus GM dBE by IB. Right. Now, what is VB by IB?
R pi.
Right. So that is the resistance R pi here, because you see that VB is the voltage across the resistance R pi, and IB is the current that is flowing into R pi. So VB, IB, R pi. So this we write here minus GM R pi. Right. And what is GM R pi? See, GM is IC by VT, and R pi is VT by IB. Right? So VT and VT will cancel out, we'll have minus IC by IB. And what is IC by IB?
Or beta.
IC by IB is beta. So we have minus beta. So that is the current gain for this common emitter amplifier. So GM pi is nothing but beta, right? Any question, guys?
Sir, can you sir repeat that part? Why VB by VS is less than 1?
Why VB by VS less than 1?
Yes, sir.
Oh my God, that's a very difficult question. Can anyone answer to that question?
Sir, I actually missed that part somehow.
Yeah, that's okay. Can anyone answer this question? Why VB by VS is less than 1? Everybody missed that part? This is VB by VS. I wrote here less than 1. Why it is less than 1?
So the value of denominator is greater than the value of numerator.
Oh, right. The value of the denominator is R5 plus RS. And numerator we have only R5. So is that correct? Does that answer to your question?
Yes, sir.
Yes. Okay. So any other question? So we have determined all the expressions for this common emitter amplifier, the voltage gain, current gain, input output resistances. Right now we try to have an idea about the range of values these parameters can have, and what is the conclusion we can draw about these values. I'm going to go to the next one. Okay, so what we have got, first of all, the input resistance Ri, we got R5, right? And the output resistance we got R0. The input resistance R5, we have this expression for R5 as Vt by Ib, right? And R0, we have this expression as Va by Ic. Right? So obviously the Vt and Va, these are constants. Vt is known as the thermal voltage, which is given as Kt by Q. Usually we take about as 25 millivolt at room temperature. And Va is a constant that varies from transistor to transistor. Different transistor can have different values for Va, but constant for a particular transistor. So let's assume that Va is 100 volt for this for our example. Now, if these values are fixed, then obviously the values of the input and the output resistance will depend on the bias current Ib and Ic. So Ib and Ic as they're related. So let's assume a value for the Ic. Ic usually will be in the milliampere range in most cases. So we assume a typical value of 1 milliampere to just have to simplify our calculation, is convenient value. So we calculate the values for 1 milliampere for these parameters of the transistor. So the IC is 1 milliampere, then IB, right? What will be IB? IB will be IC by beta, right? So let's assume that this transistor has beta 100. Then IC will be, IB will be 1, that is milliampere divided by 100. So that will give us 0.01 million, right? Any question, guys? So we assume some values, some typical values for this to calculate the input-output resistances for the common emitter amplifier. Now Vt is 25 millivolt and Ib is 0.01 milliampere, right? So what will be the value here?
Two five zero zero.
2500.
Right. So 2500, what will be the unit?
V by A.
V by A.
Yes, sir.
And what's that?
It's ohm.
Ohm.
Ohm, we call it ohm, right?
Yes.
2500 ohm, or usually we express in kilo ohms, so 2.5 kilo ohms. Right? And if we calculate the output resistance, now VA is given 100 volt, and IC is given as 1 milliampere. So what will be the resistance here?
1 kilo ohm. 100 kilo ohm.
Right, 100 kilo ohm. So what does it say about the input-output resistances of the common emitter amplifier? Is the input resistance high, low, or what? What about the output resistance? Is it high or is it low? What we can say?
Output resistance is higher compared to the input resistance.
Right. Output resistance is higher than the input resistance. So you are making a comparison. Other than that, what we can say, the input resistance 2.5, is it high or low? Now in electronic circuits, the resistance are usually given in kilo ohms. Right? Because ohm is very low for the electronic circuits. So if resistance in the range of ohm, it is considered to be very low. Right? Few kilo ohms, if it is few kilo ohms, is also considered to be low, right? Not very low, but low, few kilo ohms. And if it is, right, tens of kilo ohms, about 100 kilo ohms, right, that is considered to be high, right? And if you have several hundred, right, several hundred kilo ohms or mega ohms, right, so that is considered very high, right? Is that clear, guys?
Yes, sir.
Yeah. So from this, the definition of low and high, right? If ohm is very low, few kilo ohms is low, and the about 100 kilo ohms, so tens of kilo ohms plus is high. So from this definition, we can say that the input resistance for this common emitter amplifier is low, right? Common emitter amplifier has a low input resistance. The output resistance, we have 100 kilo ohm around this range, so that will be high. That we can consider to be high, right? And these also depend on the bus current, right? IC we have taken 1 milliampere. If you take higher values for IC, then you see that IB will increase and you will have even lower RI, even lower value for RI. And R naught will also decrease in that case. But here, right. Now, what is the implication of this Okay, and the low input resistance. What is the implication of this low input resistance? Does it have any effect on the performance of the amplifier? So we go back to our previous slide here. Go back to the next slide. So the overall gain, right, was expressed like this. This is some problem. So that was our overall gain, right? So what do we see here? It has two parts, right? This first part is this, and second part is this. You see that R pi is our basically our input resistance Ri, right? So these are input resistance. So if you have low input resistance Ri, what is the implication?
Low gain, sir. Low gain.
So, but the lower is Ri, the lower will be the value for Vb by Vs. Right? The lower is Ri, the lower will be the value for Vb by Vs. And the lower will be your gain, right? So the lower is value for this R pi, the lower will be this voltage, right? So less and less fraction of this Vs will appear at the base emitter terminal. More voltage will drop across Rs, right? You will lose more signal. The lower is the value of Ri, the higher will be the loss of the signal in Rs, right? And the lower will be your overall gain. So that has a very detrimental effect on the overall gain of the amplifier because you lose most of the signal. You lose most of the signal in Rs. High value of current will flow if Ri is low, and you will have a high voltage drop across Rs. Right? So that is the downside of the common emitter amplifier, that it has a relatively low input resistance and you lose some signal at the input side, right? And that causes the overall gain to fall. And the output side, if you look at the output side, the voltage gain, we have this R0 and RL in parallel. So if you look at this expression, so we want R0 to be much larger than RL. That's why I have already written here. The higher is the value of R0, the higher will be the gain, because then this will be, we can approximate this gain as RL, right? If R0 is much greater than RL, then this we can approximate RL and we will have a higher gain. But if R0 is low, then overall gain will be, I mean, the parallel combination, value of the parallel combination will be low and the gain will be also low. So for the output side, also we need this R0 to be as high as possible, then that will improve the overall gain. Guys, any question? Is it clear?
Yes, sir.
Okay, so that's we talked about input and output resistances. Now let's see about the gain. What is the gain? The main gain part for the common emitter. amplifier was the gain from the base to collector V naught by VE, which was GM R naught in parallel with RL. Now, let's say we have an RL, we take a convenient value, let's say 2.5 kilo ohms, right? And here we see that R naught is 100 kilo ohm from this our calculation. So we can easily say that R naught in this case is much greater than RL, and we can take the parallel combination of R naught and RL almost equal to RL, right? So this gain expression now we can write as minus GM RL, right? So the gain will depend on these parameters. One is the GM, the other is the RL. Now, what is GM? GM we can write as, what is GM? Can anyone tell me?
IC by VT.
GM is IC by VT, right? And IC we have taken 1 milliampere, and VT is 25 millivolt. Now here the GM is expressed by ampere per volt, so milliampere per volt. So we keep IC in milliampere, current in milliampere, and voltage will convert it into volt, so 0.25 volt. And then what is the result of this one?
So 40 milliampere per volt.
Right, so 40 milliampere per volt. So that is the GM, and the overall, the voltage gain from base to the collector V naught by VT is minus GM RL. GM is 40, and RL in this case is 2.5 kilo ohm, and these two together is minus 100. So common emitter amplifier has a quite high gain. With IC 1 milliampere, you get 100 gain of 100 voltage gain. If you take IC 2 milliampere, right, then you see that the GM will be 80, right, and gain will be 200. So you see, this is how we can adjust the gain by adjusting the value of the mask and IC, right? So in this IC, this is how we fix the gain, by fixing the value of IC. Now, to get high gain, you need high value for IC. So of course, with increasing the value of IC, it will demand more power, higher power, and there will be also higher power loss, because you have I square R loss in the circuit. The higher is the R, the higher is the power loss. And also with increase in IC, your RI will decrease, RI because IB increases, so there will also the loss at the input side will also decrease. So there's some trade-off you need to make, right? Or you can modify the circuit. Guys, any question? So this is how you need to understand the effect of the different parameters, how they affect the transistor, the performance, its gain, its input and output resistances, right, in order to design the amplifier that suits the particular requirement. Now, current gain, as you have seen, the current gain for the amplifier is minus beta. Usually beta is large. So common emitter amplifier also has a high current gain. So it has both the voltage gain and current gain. We say that it is high, right? For common emitter, both the voltage gain and current gain is high. And once you have determined voltage gain and current gain, you can also determine the power gain, right? The power gain, the output power, given by the input power. And output power is the output voltage and output current, and input power is input voltage and input current. Right? So that's the voltage gain, this is the current gain. So it does the product of the voltage gain and current gain, that will be the power gain. So since they both are high, both the voltage gain and current gain both are high, so you get quite high power gain. So you have a very high power gain for common emitter amplifier. Guys, any question? Guys, what is the main drawback of common emitter amplifier?
Low input resistance.
It is a low input resistance, and what is the consequence of that?
A lower gain.
That causes loss of signal at the input side, right?
Signal. Yes, sir.
Low input resistance causes loss of input signal at the input side, and that will reduce the overall gain. And what are the merits? What are the merits for the common emitter amplifier?
Sure. High voltage gain and high current gain.
It has high voltage gain, high current gain, and very high power gain. So these are the merits of the common emitter amplifier. Guys, what is this amplifier?
Common collector.
Right, this is the common collector amplifier. And we would like to determine the same parameters that we have determined for the common emitter amplifier. So we start with the small signal, the equivalent circuit. So here we'll use the I think T model will be easier. Let's use the T model. So this is our T model. Now at the input side, we add the signal source. And at the output side, we have the load. So that is our output resistance. And here this is our input resistance. The current that is flowing, this one is our input current, II. The collector is grounded. So we just ground the collector. Now, what will be the input resistance in this case? Ri. Okay, this circuit has a name. What do you call this circuit? Hello, anyone remembers? What do you call this circuit? No one knows.
So small signal equivalent circuit T model.
Right, this is called a small signal equivalent circuit. Small signal equivalent circuit. And this is for common collector amplifier. Right? So when you replace the transistor by one of these small signal models, this we have replaced this by T model. The T and pi models, these are also known as the small signal models. The small signal means when the signal is small, Vs, our input signal, when this is small, then these models we can use this model. These models are valid only when the signal is small. The main signal that we talk about here is our signal base to emitter voltage, VBE. Right? If VB is small enough, then we can use this model. These models are valid. If signal is large, then this model will fail. They do not apply. How small the signal has to be for these models to be valid? VBE, what should be the maximum value of VBE for these models to be valid? Yes. Anyone have any idea? What should be the value for VBE for the signal to be small? No idea. VB should be less than or equal to 10 millivolt. So If this is true, then we call the signal is small, right? Small signal. VB should be less than or maximum 10 millivolt, right? It can be more than that. So then these models are valid, hybrid pi and T models, and we can use these models to draw the equivalent circuit, and that's we call a small signal equivalent circuit. Okay, coming back to our main point, so we need to determine what is the input resistance RR. So what is the input resistance RI?
Sir, RE plus RL.
RE plus RL.
RE plus RL, that's it.
Oh no, sir, only RE.
Hmm?
Sir, only RE.
Only RE?
Yes, sir.
How only RE?
Sir, because RL is not part of
Hmm?
this amplifier.
RL is not part of the amplifier, but RL is there, no?
Yes, sir.
When you are determining the gain, you see that RL comes in, right? The input resistance between this point and ground. No? You cannot take a floating point, right? We are saying the input resistance at a particular point, right? So there's between this point and ground, right? With respect to ground. So here is RL is grounded, so RL will be included. No? So what will be the input resistance? Yes, guys. We are looking from the base side, right? RI resistance looking from the base side, and RE and RL, both of these are in the emitter side, right? Both of these are in the emitter side. So there will be some modification of this resistance. What modification will have? Hello guys, we discussed in the last class, you remember? You need to remember, you need to review the materials, right? Otherwise you get pretty slow. No one remembers? Do you guys take notes? Anyone taking notes now?
Yes, sir.
You should be taking notes and keep it handy so it will be easy for you to review, right? It's not always possible to, see the video. Keeping notes with you, it will be more effective. Ri is the resistance looking from the base. No, but between base and emitter, we don't have any resistance on the base side, but we have on the emitter side, we have these two resistances, Re and RL, between the base point and the emitter point. So what we will see, these resistances will be reflected into the base, and they'll be multiplied by this factor beta plus 1. So we have Re plus RL, that is on the emitter side, and that times beta plus 1. So that will be the input resistance, and that we call the resistance reflection rule that we introduced in the last class, resistance reflection rule. So it is very convenient to apply this rule to determine both the input and the output resistances, in this case for the common collector amplifier. Otherwise, you can also apply the basic definition of the resistance, which is voltage by current, which is the input resistance. In this case, the voltage at this point we can call it VB, that is the base voltage. The current that is flowing in is II. So VB by II, right? So and II is the base voltage, so VB by IB. So now you can write for expression for base voltage. So that is the voltage that is between base and ground, and VB we can write between base and ground. We have IE, we have RE plus RL, right? And that divided by IB, and IE by IB is beta plus 1. Beta plus 1, we have RE plus RL, right? That leads to the same expression. So if you would just remember this resistance equation, you know how to apply this rule, so you can straight away write down the expression for the input resistance without going through these steps, right? You don't need to go through these steps. Just apply this rule and you can directly straight away write the expression for the input. Is that clear, guys? Any question?
Yes, sir.
Is it clear?
Yes, sir.
Okay, what is the output resistance? Hello guys, what is the output resistance? So no one can tell me, okay, see that output resistance between the emitter point. Again, we have the ground, right? So we need to determine between these 2 points output resistance. And if you start from this point, you go all the way, right, here to this, the ground. So there is between ground and this. Right? So let's see, actually, we have to trace this path, right, to determine the output resistance. And along this path, we have this small R. We are looking from the emitter side, and RE is on the emitter side. So you can straight away write RE, right? And then they will have additional terms, and that will come from the resistance in the base side, right? So we're now into the base side. And in the base, what we have this RS, right? RS. And VS is our just voltage source. So we have just RS, and we are looking from the emitter side. So according to the resistance reflection rule, the RS when reflected into the emitter, so that will get divided by beta plus 1. So we'll have this expression for the output resistance unknown, which will be RE plus RS divided by beta plus 1. Guys, any question?
No, sir.
Okay, so I think today time is almost up. So we'll stop here and we'll continue from here next class and try to review all the lecture materials that you have discussed so far. Before coming to the class, it will be easy for you to follow and we can move faster, right?